Drew here with a video on the first part of Kirchhoffs laws, Kirchhoffs Voltage Law, which we call KVL for obvious reasons. KVL states that for every closed path in a circuit, the voltage along that path must sum to 0. As a practical application, let's look at our circuit here. So, for example, we'll give ourselves 5 volts. Say this is 10 ohm resistor and a 20 ohm resistor, because that's going to make math real easy for you. So first, we start off, we have a current here, I1, that comes out of the source, and then it splits. So we have I2 and I3. So to find the voltage along both these paths, which I'll highlight here, so we have one path in green this way, and if I can't change the color here, do red. We have one other path through the source to the second branch, back down, and back to the start. So for the green path, our current, I2, we can find using Ohm's law. All we have to do is say I2 is equal to 5 volts over 10 ohms, right? And what do we get? 0.5 amps. I3, similarly, we do the same voltage over 20 ohms equals 0.25 amps. Now, how did I know that the voltage is going to be the same at both these points? Well, it's the same node, right? And we covered that in the last video series. So we know V1 is going to be equal to that 5 volts for both of these currents. I get half an amp for the current flowing in the 10 ohm resistor branch and a quarter of an amp in the 20 ohm resistor branch. So let's see if that Kirchhoffs voltage law holds true by finding the voltage across both those resistors, how much it burns up. So if we do V2 will be the voltage that's burned up in our 10 ohm resistor. We have another application of Ohm's law, I2 times R1 is just going to be 0.5 amps times 10 ohms, and what do we get? Voila, 5 volts. V3 will be 0.25 amps times 20 ohms, and again 5 volts. So if we have, kind of running out of room on here, a 5 volt drop here, what we can say is let's take our hands, for example, and we can set our fingers pointing along that green arrow. So I've got my right hand following the green arrow, follows the circuit, comes up through that source. So we go up through the source, we hit the negative side, and we subtract it. So negative 5 volts, that's kind of ugly, negative 5 volts. Continue on with our hand across this branch, and we'll follow the green. So we'll come down here, and we hit that 5 volts that we burn up in that first resistor. And we hit the positive side, so we add it. 5 volts. And what do we get? Aha! 0 volts. So our law holds. And hopefully you'll be able to do the second one on your phone, because that too is 5 volts. let's go to a much more complicated example. So I've drawn out the circuit here from your notes. It's the first example in the book, or sorry, in the sheet. So let's see if that also holds true on here. The first example that we have in our notes covers the path right here in this kind of loop. So we'll start at negative 50. So let's start right here. And we'll go, up through the source. And since we hit the negative side, we go negative 50. Up through there, hit the positive side of V3. So positive V3. Down through our 23 volts here. Again, adding because we hit the positive side. And then we get to someplace a little funky. We have a negative voltage that we need to subtract, which is just the same as adding. So negative 5 volts here. And then we come back around. And this must equal 0. So from this we can find V3, right? We have on one side, the 50 will move over. So V3 is equal to 50 minus 23 minus 5. So that double negative cancels out. And what do we get for V3? But 22. 22 volts. So a note here. We have this negative 5 volts that we subtract. What does the negative 5 volts mean? Well, it's really easy actually. All it means is that if we switch all the signs here, negative, positive, it's the exact same thing, right? Because down here, if we followed that green arrow, we would just get an addition of 5 volts. Okay, so that's one loop. Let's do another loop. I think I've got enough room. Let's find the voltage along the path of, well, let's see. We don't know V1, but we do know V3. So why don't we do just the outside? Up like that, and around, and then back around this way. So again, we'll start at the source, so we can write negative 50 volts. Then we come up through the outside, plus V1, to the 10 volt drop on that resistor, plus 10 volts, over here, plus 15 volts. I'm going to run out of room, so let me drop down here. Round the corner, plus 2 volts, down to the 7, plus 7 volts, around the corner again. And here we see we have the negative 6 volts with the opposite polarity. So let's just take care of that now. Let's say our voltage drop is actually in the opposite direction. Plus, minus. So we add the 6 volts here. And finally we come to the 5 volts. All this is equal to 0. So now all we have to do to solve for V1 is the same as we did before. We have 50 minus, let's see, this is 18, that makes 20, so 20 volts minus 10 volts minus 5 volts. Oop. So V1 then is equal to 15 volts. Okay, so we get 15 volts here. Now I'll leave it to you. Pause your video, see if you can't find V2. Because we know V3, we solved it over here, 22 volts. So don't cheat, don't look at your sheet. This one will be pretty easy. See if you can't find it. And if you get it, go for voltage 4, right here. That's a really ugly 4. Anyway, that's all I have for this video. Be sure to watch the other video, which is Kirchhoff's current law, which is just as important.